Another fertilizer that's used to a great extent in the US and globally is urea. And on this slide, you see the chemical composition of urea. It is made, which is interesting in and of itself, by taking anhydrous ammonia and reacting it with carbon dioxide under intense temperature and pressure to form liquid urea. That liquid urea is cooled and pelletized to what you see in the top right-hand corner of this slide here. And so when this reaction occurs, it forms urea. It's a carbon-based product. So in nature, you can find urea or uric acid. It looks much similar, if not identical, to this compound here. When we make it as humans, even though it is an organic compound, it cannot be used for organic agriculture because it's been anthropogenically generated. The nice thing about urea is it still contains quite a bit of nitrogen, 46%. So it's a very nice product to use. It is used often. In fact, it's probably the most common source of synthetic nitrogen fertilizer that's used on the face of the planet. And there's several reasons. And maybe some of you have used urea, and if you haven't, and you want to try a nitrogen fertilizer, urea is wonderful to work with. It has a low tendency to cake. Now, maybe some of you have had fertilizers in your garage that have sat there over time and they just kind of turn into a brick, or the pellets or the prills, they're called, sort of cake or congregate. Urea, it takes quite a while for urea to actually do that. If you keep it in a nice dry place, it'll stay in pellet form for, man, years. Where I used to work, we had a big container of urea, probably 3 meters cubed, and it was present in that pelletized form for years. The other thing that's really nice about urea is there's no risk of explosion, unlike with pressurized anhydrous ammonia. The other nice thing about urea is it's very non-corrosive. You can store this in a metal container and it will take a long time to corrode the metal container, if it will ever at all, unlike other fertilizers. And it has a high nitrogen content, 46%. So it has a lower storage cost because you don't have to use wood or plastic, etc. And it has a high nitrogen content. And so the transportation cost is actually lower as well. And it's a solid, it's not a liquid. So it's attractive to utilize in production ag settings. So some properties of urea. It's, quote, organic because it contains carbon, but it also contains nitrogen. It cannot be used in organic production settings because it's anthropogenically produced. If you look at the chemical composition, do you see ammonium in it? No. Do you see nitrate in it? No. So when you apply this to a soil, it has to undergo hydrolysis prior to plant uptake. So this is what happens, right? Urea, when it's hydrolyzed, it produces ammonium and it actually temporarily increases the pH, just like we shared with you with anhydrous ammonia. And when the pH increases, there's always a risk for volatilization. So here's the reaction, or two reactions, okay? So here's urea. It will react with water, and in the presence of this enzyme called urease, which is ubiquitous, it's everywhere. It's probably on my desk. It might be on my shirt. I don't know, maybe it's in my mouth. It's certainly on the soil surface. It's on leaf surfaces. It's everywhere. When urea plus water come in contact with the urease enzyme, it forms ammonia gas and CO2. And in the soil, ammonia gas, just like anhydrous ammonia, will react with water to form ammonium plus two free hydroxide ions. And so this is what temporarily raises the pH. And if the pH goes up, there's always a risk for this reaction to go backwards, to force ammonium to ammonia above pH 7. So that tells you something about potential use of this fertilizer in terms of placement. And we'll talk about that in this section. These reactions above depend on the urease enzyme. It is everywhere. It exists naturally in soils. It's produced by soil microorganisms. And so the alteration or the reactions will take place in soils, but you need to understand placement to offset ammonia volatilization and loss of money. There are some loss pathways, right? The loss pathway of volatilization is the first thing that always comes to my mind when using urea. Why? Because if you look at the reaction, and we talked about this reaction when we talked about mineralization, and remember, mineralization was a two-step process where you take large compounds that contain nitrogen and break them down to amines and urea. And when urea is converted to the form of nitrogen that plants can use, it follows this pathway where urea reacts with water in the presence of the urease enzyme to form ammonium carbonate, which can further be broken down to ammonia gas. And eventually that ammonia gas will, if placed in the proper location in soil, convert to ammonium. So the loss pathways, volatilization, because we produce ammonium, and in the above reaction, we actually produce ammonia. And when we produce ammonium, this will increase pH. And so there's a chance for volatilization loss at each step, right? If you create ammonium and the prill of fertilizer is sitting at the soil surface, boy, it can be lost immediately. If the prill is in the soil itself, but not very deep, and it's converted to ammonium, and the pH around the prill increases to pH 9, you have a pretty good chance of losing ammonium as ammonia gas. And losses can be substantial, 25%. So the retention of ammonia in the soils with respect to urea are based on temperature, based on cation exchange capacity, as well as pH buffering capacity, and really important, placement, right? Do you just broadcast it and leave it sit on the soil surface? Or do you broadcast and incorporate to get the material into the soil itself? Or do you broadcast and immediately pray for rain or know that rain is coming so the material is washed into the soil rather quickly? Or do you simply band apply it by placing it in a concentrated band, maybe 2 inches down and 2 inches over from where you're going to plant a seed? And of course, I mentioned this already, rainfall or irrigation after application. If you apply urea fertilizer and let it sit on the soil surface for 2 weeks prior to a precipitation or irrigation event, you're taking a huge chance in terms of losing that nitrogen to volatilization. So let's take a look here at some effects on um, urea. And let's first look at temperature, right? So this is the effect of temperature on urea hydrolysis, or the conversion of urea to some other form, say ammonia or ammonium. And this is a graph that shows you time in days on the x-axis versus urea remaining in pounds of nitrogen per acre on the y. And when you apply, say, 80 pounds of nitrogen per acre of urea at 35 degrees Fahrenheit, you can see that it takes quite a while to reduce the amount of urea present to 0. At 80 degrees Fahrenheit, it reduces it at least 2 times quicker. And so temperature has a great effect on the urease enzyme and the conversion of urea to eventually ammonia and ammonia. So let's look at volatilization losses from simply a surface application of 150 pounds of nitrogen per acre of 3 different types of fertilizers on no-till corn. So we're not applying any tillage into this system. And this is a graph of a soil with a relatively low cation exchange capacity. Okay. So we're going to talk about 3 types of fertilizers here: urea, which is a solid, urea ammonium nitrate, which is a liquid, and ammonium nitrate that most producers don't use anymore. And if you look at over time, which is on the x-axis, versus volatilization loss in pounds per acre on the y-axis, where these materials were surface applied. When you surface apply urea, a solid fertilizer, the volatilization loss within a day or two is really, really high because the prill of fertilizer is in direct contact with the atmosphere, and it's likely seeing the urease enzyme and some moisture to drive volatilization. On the other hand, urea ammonium nitrate, I don't expect you to remember this part, but I want to drive home the message of urea on surface application on a low CEC soil. Okay. Urea ammonium nitrate's a liquid, so it moves readily into the soil, and so volatilization losses are low. And ammonium nitrate, it's 50-50 ammonium and nitrate, so the volatilization losses are relatively low as well. If you look at the total losses on a percent basis, we lose almost 30% of that form of nitrogen from urea based on simply applying it to a low CEC soil on the soil surface. The others are relatively low. Now let's look at another scenario. And here's the other scenario. Very similar, except now we're applying 150 pounds of nitrogen per acre in a soil that has moderate cation exchange capacity. And the scale's a little bit different on both the X and the Y axis. But when you look at volatilization losses for urea, of course, they're greater than urea ammonium nitrate or ammonium nitrate. The total losses are actually less with a moderate CEC soil as compared to a low CEC soil. And that's because there's greater places for exchange sites and the retention of ammonium in moderate cation exchange capacity soils. Let's see, these two figures tell you a little bit different story. This is a story about soil buffering capacity and the effects on pH and ammonia volatilization. And so in this system, there was surface applied urea to 3 soil mixtures with the same pH but different pH buffering capacities. Okay? And so what we're looking at here is this is days after application of surface applied urea to a soil with low buffering capacity, moderate buffering capacity, or high buffering capacity. And you can actually think of these as low CEC, moderate CEC, and high CEC. And let's look at the pounds of ammonia nitrogen per acre volatilized. So the circle is the low buffering capacity. And a heck of a lot was volatilized, relatively speaking. If we look at moderate CEC or moderate buffering capacity, relatively less, or certainly less, is volatilized, and a high buffered soil, very little is lost due to volatilization. So see, this is the puzzle. This is the soil fertility puzzle. If you knew something about cation exchange capacity, which is related to buffering capacity in a soil, and you knew what the starting pH value was, and perhaps maybe you even knew the buffer acidity from an SMP buffer, you could come up and theorize how ammonia would volatilize from the placement of urea on these 3 different types of soils, or any type of soil for that matter. Let's look at the top part of this figure, all right? And this is the change in pH after days after application. The closed circles are the low buffering capacity soil. And you can see that if we start at about close to pH 6.5, this soil ends up briefly going to above 8.5. Of course, it drops back down over time as volatilization occurs. The moderate buffering capacity soil, yeah, the pH does go up some, but there's buffering against the change in pH. And the high CEC soil, the pH does change also, but there's greater buffering against the change in pH. So this is the puzzle. This is the puzzle I want you to learn throughout this semester. And piecing the puzzle together. So another consideration in terms of loss pathways is always leaching and or denitrification after nitrification. After ammonium is held in the soil via exchange sites and it's attacked and conformed or transformed via nitrification processes through nitrosomonas and nitrobacter to form nitrate that can either be leached or denitrified, ends up in a place where you don't want it to end up. So there are some advantages and some disadvantages for using urea. The advantage, high analysis, 46% nitrogen. It's easy to handle, it's easy to ship, it's easy to use, and it's relatively cheap per pound of nitrogen, even though it's still expensive on the market currently. It's running around 850 US dollars per ton. The disadvantage is when you utilize this product, there's always a risk of volatilization, and depending on when you apply it, there's a risk for burning the seed because of volatilization and or a high change in pH, depending on the buffering capacity of the soil. So some management suggestions. These are just suggestions. If you can, apply during cool temperatures and just prior to a rainfall or an irrigation event. Anything to minimize volatilization losses with this product. If you can, incorporate it to minimize volatilization losses. Incorporating could mean tilling it in. You could broadcast and then till it in. Or you could broadcast knowing that it's going to rain within the next, 72 hours or so. Try to shoot for less than 72 hours. Or if you're using supplemental irrigation, irrigate it in immediately. Urea in the pelletized form will dissociate or dissolve readily in water. You don't want to apply this with the seed because of potential damage to the seed, because of the conversion to ammonia, which can damage the seed, or ammonium and raise the pH and damage the seed. And we typically say do not surface apply to a soil with high residue, i.e. in a system that's under no-till, where you have good residue coverage, maybe greater than 30% residue coverage, unless you can irrigate this material into the soil immediately.